Welcome to this week's third lecture in EE557. In this lecture, we are going to go into the new chapter in the book that is called Properties of Linear Stochastic Systems. This is going to start to get less conceptual from this time on, but it is still going to be mathematical, but maybe less conceptual than the earlier parts. Let us say properties of linear stochastic systems. So linearity is going to be instrumental for us because Gaussianity really propagates very nicely under linearity. So let us write our stochastic system that we're going to be dealing with. So xk plus 1 is equal to axk plus buk plus gwk. And I have yk equals to cxk plus hvk here. In this part of the course, we are going to select the input uk deterministically. Okay? So uk is selected deterministically. That means that we are considering the open loop case. UKs are given to us and we are applying it to the system. And we are making our basic assumption A. X0, W0, W1 continuing until infinity and V0, V1 continuing until infinity are independent. That is our assumption, and we know that with these two selections, we can say that the system is going to have Markov property, and all transition probabilities would satisfy a Markov type of property. Okay. In addition to this, I will assume that x0 is a Gaussian over the. It is a Gaussian over the variable x0, which means x0 bar and sigma 0 covariance. And wi, they are going to be Gaussian as well, but they will have zero mean and covariance q. And vi, the measurement noise, they are also Gaussian, let us say, with zero mean but with covariance r. And under these assumptions, we know definitely what the joint distribution of all of these variables is. So the joint distribution factorizes into marginal distributions, and the marginal distributions are given with these rules. Of course, this is true for all I larger than or equal to 0 and for all I larger than or equal to 0. All right? Now we're going to calculate transition distributions or unconditional distributions of the state and the measurement using these properties of the system. But before that, I want to actually give you the facts that I'm going to use here. So let us write facts. The first fact, and I will leave the proof of this to you. So let me say that let Z in Rn be a random vector, with, let us say that the expected value of Z is defined as Z bar, and let us say that covariance of Z is defined as sigma sub Z, okay? Z minus Z bar transpose, okay? Now we are defining a new random vector, S, which is equal to A times Z. In this case, we can easily calculate the mean and the covariance of S, and they are given to us as follows. The mean of S, it is expected value of S, is A times Z bar. Okay? If I take the expectation of both sides, then A can get outside, it's deterministic, can get outside the expectation, and I need to take only the expectation of Z, and that gives me this formula. And when I calculate the covariance of the random vector S, then that can be shown to be A times sigma Z times A transpose. Okay? Just prove this yourselves. I have done such proof for a Gaussian random variable, random vector, but the Gaussianity really is not necessary here. It is true for any such random vector Z, whatever its distribution is. The second fact that I'm going to use is related to the Gaussianity. So if I assume furthermore that Z is Gaussian, then I can write the distribution of S by using these mean and covariance equalities. So let us say that let Z be in Rn be distributed as Z normal, Z bar, and sigma Z, then we have, if we define S equals to A times Z, A is any matrix of proper size that we can multiply Z with, then this is, S is distributed as follows. A Z bar, A sigma Z, and A transpose. Okay? So the Gaussianity propagates it can propagate from linear expressions. So if you have a jointly Gaussian random variable, or if you have a Gaussian random vector, then when you take its linear function, the result is going to be Gaussian as well, and the mean and covariance is going to be given with these expressions. Let us write the third fact. Let Z1 and Z2 in Rn be uncorrelated random vectors. With mean Z1 bar and Z2 bar, and covariance sigma Z1, sigma Z2, respectively. So if we define a new random vector as the sum of these two random vectors, let us say S equals to Z1 plus Z2, then I can actually show that the mean of S, which is S bar, is the summation of the means of these random vectors plus, actually for this equality to hold, uncorrelatedness is not required. So this type of equality would always hold for any Z1 and Z2, even if they are correlated. So, but here I want to actually give another equality here, which is only possible when you have uncorrelatedness. So when I look at the covariance of S, then it's going to be the summation of the covariances of Z1 and Z2. And for this second equality, uncorrelatedness would be actually required. Okay? Why is that? So I told you that I'm not going to go over the proofs, but let me try to show you what is happening here. So as I told you, the mean of S would always be the summation of the means of Z1 and Z2. Expectation can always be distributed over the summation here. It's a linear operation. And if I look at S minus S bar, then this is going to be Z1 minus Z1 bar plus Z2 minus Z2 bar. Okay? And what is the covariance? Sigma S is nothing but expected value S minus S bar transpose. Then I can substitute these summation into this S minus S bar. So I have Z1 minus Z1 bar plus Z2 minus Z2 bar. And I have the covariance of the, transpose of the same thing. Z1 minus Z1 bar plus Z2 minus Z2 bar transpose. Okay? So you see that such a covariance calculation would have 4 different terms. Multiplication of Z1 minus Z1 bar with Z1 minus Z1 bar transpose. That is going to be sigma Z1. Okay? Multiplication of Z1 minus Z1 bar with Z2 minus Z2 bar transpose, expected value. It's going to be 0 due to uncorrelatedness. Okay? Due to uncorrelatedness, I can divide that expectation into 2 parts. Expectation of Z1 minus Z1 bar times expectation of Z2 minus Z2 bar transpose. But those expectations would be equal to 0. And actually that is the covariance, cross covariance of Z1 and Z2. Therefore it is equal to 0 by the uncorrelatedness assumption. And therefore the cross terms are both equal to 0, but I have the square type of terms here, which would give me sigma Z1 and sigma Z2. As a result, when you have the summation of uncorrelated random vectors, covariance of the sum is the sum of the covariances. Okay? So the covariance operation can be distributed over in individual summed variables here. So this is going to also mean that for independent random vectors, I would have the same property. Because independence implies uncorrelatedness. And uncorrelatedness provides us with this property. That means that for independent random vectors Z1 and Z2, I would also have the same property. Okay? So these are the facts that we're going to use. The ones that I did not prove, please try to prove them yourselves. So now let us go back to our system here and let us try to obtain some concepts that we have seen in the past. So let us look at the transition function. This is a stochastic system, but I can still define a transition function by considering the input U and the disturbance WK as the new inputs. So here let me write xk plus 1 is equal to AXK. This is a time invariant linear stochastic system, but with the time varying system, then I would have AK, BK, GK here. We are not going to consider that one because it's significantly more complicated, the expressions, but the expressions could still be derived for the time varying case as well. AXK plus BUK plus GWK. Now I will write xk plus 2. xk plus 2 is equal to A times xk plus 1, which is this, AXK plus BUK plus GWK plus I have BUK plus 1 plus GWK plus 1. Okay? If I expand this part here, I would have A square xk plus ABUK plus BUK plus 1 plus AGWK plus GWK plus 1. Okay? So you see that here I could write xk plus 2 as a squared times xk, and I have some input terms, input uk and uk plus 1, and I have the disturbance terms here, wk and wk plus 1. If I do the same thing for xk plus 3, let us try to obtain the terms. I would have a cube xk, okay, plus, in this case, I would have a power 1 less than this one, a squared buk plus a buk plus 1 plus buk plus 2, and I have the disturbance terms, a squared gwk, agwk plus 1 plus gwk plus 2. Okay? So you see that we can write any xk plus I here in this form. So now let us try to write the general function. Xk plus, I would say, m is greater than or equal to 1, I can think about it like that, is equal to a to the m xk plus, here I'm going to put a summation over when I is going to continue from 0 to m minus 1. Okay? And I would have here uk plus I. There would be some multiplying matrices here in the front. And I would put another summation, I from 0 to m minus 1. And in this case, I would have, again, wk plus I. And I would again have matrix multipliers. So you see that when I is equal to 0, the power of A, first of all, there is always B in front of you. Okay? So I would always have B. Similarly, there is always G in front of W. Okay? Now I have to adjust the powers of A appearing here. At I equals to 0, the power should be I minus m minus 1. M is 3 here, and the power here is 2, which is m minus 1. At I is equal to m minus 1, when I is equal to 2, the power of A should be 0. That tells me that here I need to have the powers of A decreasing when I increases. Okay? So I need to have m minus 1 minus I here, and I need to have m minus 1 minus I. So you see that when I is equal to 0, the power is m minus 1, and when I is equal to m minus 1, the power is 0. And in between, you have the powers in between. Okay? So the right-hand side here is nothing but the transition function of the state. This is f from k to k plus m. It's a function of xk, and I have uk from k plus m minus 1 and wk from k plus m minus 1. Okay? So we can find our transition function in this manner. But we know that such transition functions are not really useful for us with the stochastic systems because of the unknown terms here, w's. Okay? That is why instead of calculating these transition functions or dealing with these transition functions, we are going to calculate transition PDFs here. So let us now try to look at transition PDFs. So I want this transition function to remain here, or maybe I should write it in a corner. Let me write it here. xk plus m is equal to a to the m xk plus I from 0 to m minus 1, a to the m minus 1 minus I, uk plus I. in some way it is good if you can memorize this expression so that you don't deal with the same thing over and over when you want to use this type of thing. So I have I from 0 to m minus 1. So I have here b, a to the m minus 1 minus I, g, w, k plus I. Okay? So this is our m-step transition function. And now we can utilize that formula in order to be able to obtain the transition PDFs. So let us look at transition and output. These are conditional PDFs. Okay? So the first thing that I'm going to do is to obtain the one-step transition PDF, xk plus 1, given xk and uk here. What is this distribution? I have actually done such operations in the previous lectures on some examples. Now I'm going to do the general case, and I won't repeat it for the m-step case, etc. Okay? So if you want to derive the m-step distributions, I will here write directly the distribution using assuming that I did all of these steps. But here I will just do the one-step transition PDF in this lecture. So here, in order to be able to calculate this PDF, I need fxk plus 1 given xk uk evaluated at psi k plus 1. This is the cumulative distribution function, and we know that this would look like, this would by definition equal to the probability xk plus 1 smaller than or equal to psi k plus 1 given xk uk. Okay? We know the recursion for xk plus 1, or you can substitute here m equals to 1. In that case, you would just get this equation. Okay? Then I can actually write this thing as p, and I would have axk plus buk plus gwk given xk and uk. I can, sorry, this is wrong. I have forgotten the inequality. Smaller than or equal to psi k plus 1 given xk uk. Okay? I can, xk and uk are given, so these are nothing but deterministic variables. I can take them to the other side. gwk smaller than or equal to psi k plus 1 minus axk minus buk and given xk uk. But here now this event, if I keep this right hand side, this event is only related to wk or gwk, which is independent with xk and uk. Because in xk, I have only w's from 0 to k minus 1, and I only have x0. I see that gwk would be independent with these variables. That means that this is just p gwk psi k plus 1 minus axk minus buk and no conditionings. But this is nothing but the cumulative distribution function of this gwk random variable or random vector. Okay, so I can write this as f gwk, and inside this f gwk I have substituted this psi k plus 1 minus axk minus buk. Okay. Now I can actually, here, if you don't sometimes it is easier to set gwk to another variable like wk prime and then you can work it out with that definition. But here I'm not going to do it. So I will just write f of, maybe I shouldn't write it. So I have here this cumulative distribution function of xk plus 1 given xk and uk is the cumulative distribution function of gwk evaluated at this deterministic number. Okay? So here I will take the derivative of both sides, which is going to give me the density that I am after. So I have xk uk. This is going to be the distribution of or PDF of GWK evaluated at, instead of psi, I will substitute xk plus 1 here, minus xk minus BUK. Okay? So we see here that in order to be able to find this conditional PDF, I need to find the distribution of GWK. Okay? So WK is itself normal with zero mean and covariance Q. Then what would be the distribution of GWK? It would be zero mean, G times the mean of W, it would be 0, and covariance would be GQ G transpose. So you need to be able to do this type of manipulations in your mind quite quickly to continue with this course. Okay? So that is GWK distribution, and now instead of GWK I will substitute this quantity inside the parentheses. Okay? Let us do that. So I have P xk plus 1 given xk uk is equal to normal. Instead of GWK, I'm substituting this. Maybe I should write down below. That is equal to normal. I have xk plus 1 minus axk minus buk, and I have the mean 0 and the covariance GQ G transpose. Okay? If you have a Gaussian distribution of this form, you can always take these parts to the mean here. Okay? So this Gaussian distribution is nothing but in the exponential, I have this quantity minus the mean 0 squared. But I can interpret that parenthesis here as this number minus this mean squared. Okay, that is the same thing. So I can write this as normal xk plus 1 with mean axk plus buk, and I have the covariance GQ G transpose. So that tells us our result here. One step transition PDF pxk plus 1 given xk uk is just this. So I have a Gaussian with over the variable xk plus 1, and the mean is axk plus buk, covariance is GQ G transpose. Okay? So this result also tells us what the conditional mean of this distribution is and what the conditional covariance of this distribution is. So I can write these results. Expected value xk plus 1, xk and uk would be this mean axk plus buk, and the covariance of xk plus 1 given xk uk is GQ G transpose. Okay? So the result that we find covers all of the expectations given, conditional expectations given like this. So those expectations and covariance formulas, actually, they do not require Gaussianity. The only result that we found so far that would require Gaussianity of the process noise is this result. The transition PDF is Gaussian because of the Gaussianity of the process noise. But the expectation and the covariance formulas, they do not require Gaussianity, and I would like to show that to you. Maybe I shouldn't have erased this formula. Sorry. So here we are talking about this expectation, xk plus 1 given xk and uk. This is equal to expectation of xk plus 1 is axk plus buk plus gwk. Okay? And xk and uk are given to us. So now I can distribute this expectation over the sum here, axk given xk uk plus expected value buk given xk uk plus expected value gwk xk uk. So now I would like to calculate the expected value of axk when xk is given to us. Okay? When xk is given to us, this quantity is deterministic. So it gets out of the expectation directly, axk, plus similarly for this one the same, buk, plus we see here this expectation. We know that wk is independent with xk and uk. uk is actually deterministic. It has no relationship with any of the random variables here. But xk contains previous w's from 0 to k minus 1 and x0. But x0 and the previous w's are all independent with wk. That means that this is nothing but expected value gwk itself. I can remove these conditionings. G can get outside, and I would have expected value of wk itself, which is 0. So that would give me, this is 0, axk plus buk. So here you see that I didn't use the Gaussianity of wk at all. Okay? I have just used here the zero mean property of wk. Okay? So wk could have any other distribution than the Gaussian distribution. As long as it has zero mean, then I would have the same expected value property here. So this expected value property is independent of the Gaussianity property of the process noise. As long as the process noise has zero mean for all time instants, I would have just the same expression here. What about the covariance? So this is my mean for conditional mean, and let us write this covariance. Covariance of xk plus 1 given xk uk is expected value xk plus 1 minus the conditional mean of this thing, which is this, axk minus buk times the transpose of the same quantity. Sometimes, in order not to repeat the quantities here that I write, instead I will just write this. This means this thing on the left, transpose, okay, given xk and uk. This is the conditional covariance of the state xk plus 1. If I subtract axk plus buk from xk, you see that we are going to get expected value of gwk times the same thing here, gwk transpose. And I have in the given condition xk and uk, but we know that these conditions do not mean anything for wk. that means that I need to calculate only the expected value of WK transpose G transpose, and this is nothing but expectation can be taken inside of this matrix multiplication. G expected value WK transpose G transpose, but this is nothing but GQ G transpose. So you see that here I really did not use the Gaussianity of the process noise. So what I used is the independence assumption. Independence can come with any marginal distribution. So even if these are not Gaussian, I can say that the random variables are actually independent, and I use the independence assumption plus the zero mean property plus the covariance Q property of the process noise. Okay? So we see here that these two equalities would be satisfied as long as we have a linear system and we have this mean and this covariance for the process noise with the independence assumption. Okay? Process noise can have any distribution, and these two properties would hold. Obviously, this property would not hold in that case, because if the process noise is not Gaussian, then this distribution is going to be that non-Gaussian distribution, and therefore this equality would not be satisfied with non-Gaussian process noise. Okay? So this finishes the one-step transition probability case. Now we can go into m-step transition probability case. And for that, I'm going to require that I have written the equality that I have written and erased onto that corner. Let me write it once more, sorry for this. xk plus m is equal to a to the m xk plus so this is our m-step transition function. And now what we would like to do is to calculate the m-step transition probability. xk plus m given xk, uk from k to k plus m minus 1. Okay? What is this transition distribution? In this case, I'm not going to calculate this PDF in the long way. Okay, you can do it yourselves. I have done it over and over in this and the previous lectures. So here, I will just think about that it is going to be Gaussian. xk is given to us, and these uk's are given to us. So the only randomness here is going to be due to this process noise. Okay? And these process noises that I write here, they would be, all of them would be independent with xk and all of these inputs. Okay? So here, I can actually write the conditional mean as follows. Expected value, xk plus m, given xk and uk given from k to k plus m minus 1 is going to be, I'm going to take the expected value of this. It's going to be a to the m xk, because xk is given to me. And all of these inputs here, they are given to me. That means that the expected value of these terms would be just this, m minus 1, a to the m minus 1 minus I, b uk plus I. and expected value of these noise terms. All of these noise terms would be independent with xk, and uk's are already deterministic. I don't have to care about them. That means that I need to take only the expected value of these wk's, given nothing because of the independence, and these expected values are 0. So the means are given like this. So you see that I didn't use Gaussianity at all here. Again, Gaussianity of the process noises were not used. The second thing is going to be the covariance of xk plus m given xk and uk k plus m minus 1. In order to be able to do that, I'm going to subtract the conditional mean of xk plus m from xk plus m, okay? And then I will calculate the covariance of the remaining term. The expected value, so what I need to do here is this. Expected value xk plus m minus, I need to subtract the conditional expectation xk plus m given xk uk k from k to k plus m minus 1, and I have here this thing, close the parentheses, and then the same thing transpose given xk uk from k to k plus m minus 1. Okay, I need to calculate this expected value. So what I'm going to do is that subtract this mean from xk plus m, and we see that these terms are going to cancel, and the only remaining term would be this, and that is expected value I from 0 to m minus 1, a to the m minus 1 minus 1, I, g, wk plus I, and this thing times its transpose. Okay? Now what am I going to do with this thing? So this is like the covariance of this summation of these noise terms, these weighted noise terms. All right? So this is something like covariance of, we know that the mean of these terms are all 0. So this is like covariance of this summation. I from 0 to a m minus 1 minus I, g, wk plus I. Okay? This is the covariance of this summation. By the way, you see that here, I just dropped automatically. I didn't do it intentionally, but here I dropped these given conditions from here, from this expected value, because the noises here, they are wk plus 1 going until wk plus m minus 1. Here these noise terms, they are all independent with these variables, so I can make this dropping of this conditioning. Okay, I didn't do it intentionally here. This was a mistake here, but fortunately it turned out to be true. Okay, that is correct. So we can remove these conditionings when we go into the W variables here. So now I have the covariance of summation of some noise terms. I know that these noise terms are all independent from each other. Okay? That means that I can actually distribute the covariance operation over the summation. So I can replace summation with co. I from 0 to m minus 1, co a m minus 1 minus I, g, wk plus I. Okay? Now I know how to calculate this covariance. This is a matrix times a Gaussian variable with Gaussianity is not really important still. I have 0 mean and covariance q random vector here. So this is going to be I from 0 to m minus 1, and the covariance of this thing is going to be this matrix m minus 1 minus I, g times the covariance of wk plus I, it's q, and I have the transpose of this matrix, G transpose, A m minus 1 minus I transpose. Here the transpose can always be interchanged with the power operation. It's really not a problem. So we see that this is the conditional covariance, and you see that here I didn't require, this expression really does not require Gaussianity. The only thing I require here is the covariance of W. So if W was not Gaussian but it had covariance Q, then this equation would still be correct. So now this is the expected value and the covariance. Then what is this distribution? If you do it the long way, if you calculate the CDF and then take the derivative to calculate that PDF here, you're going to see that it's going to be, again, Gaussian. So you're going to end up with the distribution of these summation of noise terms, and this summation of noise terms have zero mean and the covariance given with this expression, and then you will substitute xk plus m minus xk minus a to the mxk minus these terms into that distribution, and it's going to give you another Gaussian distribution. So here, this transition distribution, it's going to be pxk plus m, and I have given xk, and all of these inputs, from k to k plus m minus 1, they are going to, the result is going to be a normal distribution over the random vector xk plus m. The mean is going to be this thing. A to the m minus 1 minus I, b uk plus I. This is my mean, and the covariance is going to be just this. So here I will show you that transpose and the power can always be interchanged. Okay? And this is going to be just this Gaussian distribution. So here, as I told you over and over here, we don't require Gaussianity for these two expressions, but this last expression, of course, requires Gaussianity. Okay? So here, an interesting thing also is that the covariance of this transition distribution, the covariance of this m-step transition distribution, it really does not depend on the input at all. Okay? Because the input was deterministic here, when I subtracted it from the variable itself, the covariance did not include any term related to the input. That's one remark that we can make. So this finishes our finding the transition PDFs. This time I will keep this. So we are done with the transition PDFs, but now we can look at the conditional PDFs of the output. So I have the output equation given like this. What is the distribution P yk given xk? Okay? Let us try to find this distribution. In this case, really, it's not going to be difficult. It is again going to be Gaussian. This term is already given to us, and this term is Gaussian distributed with mean 0, and the covariance H transpose. So this is going to be a normal distribution. The argument of the density is yk. The mean is going to be cxk, and the covariance is going to be H transpose. So that means again that expected value yk given xk is nothing but cxk, and co yk given xk is again H transpose. All right? Remember that we call this thing as the likelihood. So if you remember our discussion, our alternative description of the stochastic process, so I have xk plus 1 is equal to a xk plus buk plus gwk when I have also the distribution of wk as 0 and q Gaussian like this, then I could replace both of these equations with this transition density given like this, xk plus 1 given, not given, so I have axk plus buk and gq transpose. So we see that this transition distribution, one-step transition distribution, has the same information as these two equations. Similarly, the output equation, instead of specifying the output equation like this, cxk plus hvk, and specifying the noise distribution as 0r, normal 0r, we can summarize this information over with single likelihood here. Normal yk, cxk, and h are H transpose. So these informations here, they would be equivalent to each other. Instead of writing this, I can write only this transition distribution, and instead of writing this, I can only write the likelihood. And they would give us the same amount of information. Okay? So here I think I have filled my time now. In the next lecture, we are going to continue by finding the marginal PDFs of the states like this. Unconditional PDFs in this case. What we have found so far is the conditional PDF. P of xk given xk plus 1 given xk uk. We have found so far these conditional PDFs, but it is also possible with the linear Gaussian system to actually find these marginal PDFs. We are going to see that this is also going to be a Gaussian over xk, which mean xk bar, and the covariance that we are going to call as sigma k. Okay? And when we find these unconditional PDFs, then we are going to concentrate on how these covariances of the state and the means of the state would evolve in time. Okay? What is that going to give us? So we have a random process, x0, x1, x2, going until infinity, and this random process has a mean xk, x0 bar, x1 bar, going until infinity, and it has a covariance, sigma 0, sigma 1, sigma 2, etc. We are going to ask ourselves the following question. Is this mean and is this covariance, are they evolving into some constants or not? Okay? What does that mean? So as time k going to infinity, as time k goes to infinity, what happens to this mean and the covariance? Sometimes we are going to see that under some conditions, these mean and covariance, they're going to go to constants. So the mean of the process is going to be constant, and the covariance of the process is going to be a constant as time k goes to infinity. And in that case, we are going to say that our state process, xk, goes to a stationary process in that case. Okay? In general, such a discrete equation, it would model a non-stationary process, because because here the mean of the process and the covariance of the process might change in time. That means that the process is not even second order stationary, or white sense it's not even white sense stationary. But we are going to see that under some conditions on this A matrix and under some conditions on this G matrix, actually maybe stationarity is only related to the A matrix. We're going to see that under some condition of the system parameters, our xk is going to converge to a stationary or white sense stationary process actually. Okay, and in that case, we're going to see what type of covariances that this covariance of this process is going to converge to. All right? And we're going to use some concepts coming from control theory, like the stability of the A matrix or reachability of A with some matrix related to the G matrix. And I will try to explain those conditions as clearly as possible, because I'm not assuming that you have taken a linear system theory course before, like 502. Okay? But that is going to be all for this lecture. In the next lecture, we're going to start calculating these marginal distributions of the state, and then we will see the rest. That's all for this one. Thank you very much. Bye.